Hello and welcome to the Smart Building series. This is where we're up to now, our 7th free webinar of 2019. So today we are talking about why is brick a game changer for smart buildings? And I'm very pleased to have some people on the line from the Brick Consortium. So first of all, it's Gabe Fierro from University of California, Berkeley, and Jason Coe from UC San Diego. So hi guys, welcome.
Hi, thanks. Should I just start then?
No, I'm just going to do a first bit of housekeeping, and then we can get started with your presentation. And maybe also like a bit of an introduction to start with about brick and what you guys are doing with that schema. So just to everybody listening out there, first off, if we go through this presentation, that's the way it's going to work. We're going to get a half an hour, 40-minute presentation on what brick is and how it's going to be useful for smart buildings. And then afterwards, we're going to open it up to questions. So it should be around 10, 15 minutes for questions. If you guys type them in, I'll get those here, and then I'll be able to put them through to the people who are presenting today. Beyond that, of course, as always, we're recording this content, and that's going to be posted on our YouTube channel and also on SoundCloud, and you can even subscribe through iTunes. So if you just do a search for us, the Smart Building series, you'll find us on either SoundCloud or iTunes, and you can subscribe to all the content we do. And then, of course, beyond that, if you look, I've added a white paper that we did with brick earlier this year as a handout. So you should be able to see that in your console, and you can download it now. So yeah, now I'm going to hand over to Gabe and Jason. Guys, take it away.
Great, thanks very much. So my name is Gabe Fierro. I'm a PhD candidate at the University of California, Berkeley, and I will be speaking first about brick. So we have quite a number of slides here, so there will be a couple of them that I will sort of gloss over a little bit, but we will make sure that the slides are on our website, which is linked on the first slide here, so that you have them as a reference. So starting off, to sort of set the stage of the family of topics that we're talking about, here is sort of from the hardware on up, the set of physical resources in the building, the sensors and equipment, become grouped and encapsulated into buildings of various use cases: residential, office, commercial, industrial. On top of the buildings themselves, in the smart building space, you typically have a family of management services that are implemented: data storage, control services, monitoring services, alarms. And then on top of those management services, you have your applications, your demand response, fault detection, occupancy models. And what these do is what we're typically talking about in the realm of smart buildings is the integration from the hardware all through a higher level application that gives us insights into how the building is operating and behaving, and allows us to leverage things like big data and machine learning to more efficiently operate that building. The problem today is that when you're actually doing this development, is that there's an incredible amount of heterogeneity in the actual hardware and deployment settings. Every building site is essentially a one-off. You have the multitude of equipment vendors, BMS vendors, all with different features and capabilities. The actual deployment and configuration of these BMS and SCADA systems is often custom to the actual deployment site. Of course, on top of that, custom controls, architecture, use cases. And what's making this all work is that this is all changing over time, right? The building as it is designed is different than the building as it is built, which is different than the building as it is operated a month or a week later. And so the challenge is going to be, how do we account for this heterogeneity? The problem with accounting with heterogeneity is that it's essentially a form of fragmentation. And to deal with this requires interoperability standards. In 2004, there was this great study by NIST that showed how the lack of interoperability standards, they estimated the cost for the capital facilities industry at around $16 billion per year. And there's a more recent study by the Department of Energy looking at, when people are actually want to be deploying energy efficiency software or more efficient building operation techniques, it's actually very, very hard to estimate the impact of these techniques because it's so hard to deploy them. Every time we want to deploy a new piece of software on a building, it requires an incredible amount of manual effort to go in and tune and tweak and customize that software so they can actually understand the resources that are there in the building. It could make use of the various equipment and APIs and data sources and whatnot that are actually available in the building. And so what we have to bring to bear is a technique that's been, long established in the computer science domain, which is that of abstraction. Abstraction is key to interoperability. And what abstraction is essentially the removal of irrelevant details to focus on the properties or attributes of a problem that are relevant to a task. And this is crucial to any sort of scaling. If we ever want to scale up smart buildings, cutting edge energy efficiency techniques, we need abstraction to be brought into the smart building space. And so one form of this is shipping containers. Before shipping containers, you had to worry about what the shape and size of all the different things you wanted to put onto boats. Now that we have shipping containers, you just put it inside, and the rest of everything around that, the cranes, the boats, the storage facilities, all of that can just worry with the abstraction of the shipping container rather than the details of what's inside. This is the same thing we see with the internet, with the internet protocol being introduced to abstract over all the multitude of independently developed proprietary communication protocols that existed before that. USB as a universal bus for connecting all sorts of peripherals, and of course operating systems that allow us to run Windows or Mac OS X on top of a laptop without having to worry about what kind of chip, what kind of hard drive, what kind of keyboard, what kind of Wi-Fi card. All of that is abstracted away from us. Bringing this to the context of buildings, a lot of our telemetry right now resides within data silos. These are proprietary vendor-specific data repositories that have their own APIs, their own labels for describing what that data is. And there really isn't a common data representation. What you have today are the descriptions of buildings when you go to a BMS or you go to a database. You have these informal and ad hoc labels. On the right here, I've pulled a screenshot from a document that attempts to standardize a few of these. And I'm sure if any of you in the building space, you're probably familiar with, looking at DPR as an abbreviation for damper, but sometimes, these are misspelled. Sometimes someone has a slightly different convention, DMPR for damper instead of DPR or DMP. And so convention is normally fine for humans, right? We can take a look at an arrangement of letters and we can spot patterns and we can figure out what something is based on the conventions and our implicit knowledge of how these buildings are put together. But this is actually quite difficult for machines to make any sense of. And when you only have these sort of human readable and informal labels, it's very difficult to actually develop interoperable software on top of that. And so for this presentation, we're going to be focusing on the kind of information that gets brought out by point labels and what is described by point labels. And so to sort of go over the problem introduced by point labels. So your points, the name point in the building is typically the sensor, the actuator that's producing the digital data about the building. And these, what these points do is they combine different aspects of the building into a single name. They combine location, function, the related equipment, subsystems, process, and all sorts of related metadata in a single label. And the correct interpretation of this requires, knowing not only the site-specific conventions, but also having a good, solid understanding of the domain knowledge of how buildings actually work. And what further complicates this is that whatever the established conventions are, these are not consistent across buildings, but they're also not consistent even within an enterprise or within a building. And so an example here of a point label from the Berkley campus, this 14 to 16 character tag incorporates the air handling unit, the air handling unit identifier, the fact that there's a zone, the fact that there's a set point, and all of this implies, a greater set of equipment and points that are there. The fact that if there's a set point, there's probably a sensor. There's a VAV box in here that's not being realized. And so the point label itself is really not a sufficient descriptor for the kind of information that we want to get out of building. And so what we're talking about is essentially building metadata. Metadata itself is a term that means data about data. And in buildings, this really means sort of the collection of the following that I have on the slide: the origin and context of collected telemetry, the sensor, the set point, or whatever the register is that produced the data, the equipment or the substance that's being controlled, monitored, or regulated, the location of the data source, its physical location, the logical location, position in a process or subsystem, and related points and equipment, etc. And so we can imagine a zone temperature sensor here. It really only has significance in the context of all the rest of the stuff around it. The fact that it's in a room, that room is in an HVAC zone. That room has return and supply dampers that feed and return air through a VAV box. There's fans, there's pumps, there's an air handling unit at the top of that. And when we only look at the sensor, all the rest of that is implied. But what we're going to do here is try to bring that forward. So we're not the first people to, at the Berkley Consortium, we're not the first people to address this problem. There's definitely existing interoperability standards that we've started to work with. One very well-known one is the industry foundation classes, which is a form of building information modeling. And what these are designed to do, what IC does, is it standardizes data exchange across the design and construction phases of buildings. It focuses on geometrical modeling for space management, asset tracking. It makes it easier for architects and building designers to sort of work together. There's even sort of work that brings the IFC model forward that helps you run energy modeling and start doing iteration on your control software. There is a little bit of a data dictionary that they define for the different types of sensors, but largely IFC is not intended for the continued operation and management of the building. The data model is largely inextensible. It's very hard to add new things, and it's not the kind of data model that's very easy to query from software. Another data interoperability standard that you're probably familiar with is Haystack. And what Haystack has done is they've taken these loosely formed point labels that are typical of buildings, and they've created a tagging system around them. So instead of having sort of a binder somewhere with all the abbreviations of what the different parts of the point names mean, you can now structure those using a set of tags pulled from a dictionary. So, and Haystack does a fantastic job of doing this. They've really pushed the state of the art in terms of bringing those point labels forward into a software and digital representation that can be used. But for our purposes and for what the application that we were trying to do, we found that it wasn't quite sufficient. There was a limited notion of relationships, which I'll go over momentarily, and a lack of rules for how you're supposed to put these tags together. And while it's undoubtedly an improvement over unstructured labels, it wasn't, the tag dictionary itself did not fully cover the range of equipment and points that we wanted to talk about, and it wasn't enough to represent the structure of the subsystems and equipment within the building. And so in 2015, there was a study pulling around 90 applications from the building science literature, covering these 8 categories of applications. And this covered sort of state-of-the-art advances in modeling and control, as well as standard industry practices. And what this paper did is it decomposed each of these applications into the set of entities and relationships. So the entities required what things does the application refer to. If you have a thermal modeling application, you're referring to sensors and set points and thermostats and zones and rooms. If you're talking about, we also looked at the relationships required. How did the applications associate and find these things? The sensor is inside a room. The thermostat is, has a set point that controls the temperature of a room. And what they found in this study, and we've linked it down here, and it's also available on our website, is they found that these existing standards did not actually meet the requirements of those applications. They were not able to identify the entities that were required, nor were they able to represent the relationships or the connections between these entities. And so what this did is it asked us, it had us ask the question, what are the properties of an effective metadata standard? And what they are is we need to be able to represent the things in the building, the physical things, the virtual things, as well as the logical things. It's not just equipment and points, but it's also the software that controls the building, and it's also the particular assortment of equipment and points assembled for a particular process, such as heating, air, monitoring electricity. We also needed to represent the relationships between things, the fact that some things are contained within other things, or some things take effect before other things in some process, such as a valve needing to be opened before the hot water can heat up some air, or one fan occurring in a process before another fan. Things affecting other things, the hot water coil heating the air up, things fitting together to form a larger whole, the fact that an air handler unit, the VAV, your dampers, your return fans, your exhaust fans are all assembled together into the HVAC system or the air leak. We also needed an extensible classification of things. We were never going to be able to write down the complete dictionary of every single equipment and points that would ever exist within a building. And so while we needed concrete named definitions to be able to say, well, what is a VAV, to be able to go and look that up, but we also needed to be able to add our own definitions and expand existing ones. So as the set of equipment and points in the world grows, as these manufacturers innovate and create new equipment, we need to be able to describe the capabilities and features of that equipment as they become deployed in buildings. And lastly, we need portability and consistency. And this is what determines sort of the sufficient abstraction to allow this metadata standard to scale. Consistency means that if two people are going to describe the same building, or they're going to describe very similar buildings, those models should look very similar. Without consistency, then we're back to sort of square one, where every single building is its own unique model. And so we need mechanisms that allow consistent modeling of what is inside these buildings. What consistency gives us is also portability. The fact that relationships and these classifications should be generalizable to new situations. I should be able to discover, I should be able to, when I write an application that performs some analysis on a building, that application should be able to figure out what kind of capabilities are inside that building, what kind of equipment and points are there, and customize its operation to the particulars of that building. And so this brings us to the development of the BRIC metadata standard. And so in a few lines, BRIC is a graph-based metadata standard for smart buildings. It captures the physical, logical, virtual entities in buildings. It defines those entities using an extensible class hierarchy, and it's able to capture the necessary relationships between those entities. And so BRIC started from the 2015 BuildSys conference, where there was a collection of universities working together. We all realized that metadata really was a problem, that we were all coming up with these ad hoc solutions for how to standardize and digitize the metadata that exists in buildings today. We established a working group of universities and a few companies to work on this metadata together. And this workshop was predicated on, you needed to bring a building. You need to do a point dump on a building and do some sort of initial classification of that itself. From this, we developed the initial BRIC class hierarchy and relationships. So BRIC, as the first version of BRIC, was derived entirely empirically from actual BMS points and equipment. The relationships and classes we chose were driven by the 2015 studies that I mentioned earlier, and we cross-validated the structure by actually going and implementing those applications against real buildings. And what BRIC is today is it's evolved from this structure, but it maintains this foothold in empiricism, the fact that we are really trying to describe the entities and relationships that application developers have actually had to describe, rather than just trying to posit what those might be. And so I'm going to go over a few of these core brick concepts. Firstly, the concept of an entity. This is the abstraction of any physical, logical, or virtual item. These are essentially the things in a building. So here's a few examples. We've got a thermostat, an air handler unit, the sort of floor pan rooms are things, as well as the HVAC zones, the logical collection of a set of rooms, as well as things like controllers and pitches. These are all things. A relationship defines the nature of a link between two related entities. So this is something, this is along the lines of encapsulation, the fact that a thermostat might be located in a room, the fact that a air handler unit is upstream of a VAV box, or even the fact that a thermostat is a thermostat. The notion of a thermostat as a generic class of objects, that class is a thing, and that thermostat is also a thing, and the relationship between them is that one, the type of one is given by the other. This is a bit of a meta modeling problem, but we'll make this more concrete as we go forward. A class is a named category with some intentional meaning or definition that's used for grouping entities. We happen to organize classes into a hierarchy, and our entities, the actual things, are going to be instances of one or more classes. So here's an example of a class of the class of blowdown water, which defined by water expelled from a system to remove mineral buildup. It has a superclass that is given by water, so we could go and look up the definition of water. And so anything that is of type blowdown water is also going to be of type water. And here on the right are the set of root classes that we've defined at Brick. So we have a hierarchy for each of these. We have a hierarchy of equipment, hierarchy of points, hierarchy of locations, a hierarchy of substances like water, and a hierarchy of quantities, things like temperature and CO2 levels. The last concept, the last high-level concept I'm going to go over is the idea of a graph. A graph is an abstract data structure that represents a set of entities and the relationships between them. So here the nodes are the circles, the node labels, which are going to be the names of the entities or what's written inside the circle. The edges here are directed. They have an arrow. So here C points to B, A points to B, B points to D. Edges have direction and edges have labels. And so in the context of a relationship, the relationship name would be the edge label, and C would have the relationship CB to the node B. And what we'll do later on is we'll replace these labels with the actual entities and classes and relationships in Brick. But this is just a high-level overview. This is just a reference slide with all of this definition. And so now we're into the Brick class hierarchy. So this is just a small subset of it, but we can see sort of the kinds of equipment. So we have equipment categorized by fire safety system, HVAC. There'll be electrical monitoring, lighting, and so on. Points are categorized by a few high-level classes: command, sensor, set point, alarm, and so on. We have a few. We have a similar hierarchy for location, similar hierarchies for resource and substance. And so having this class structure makes it much easier to discover the set of classes that are actually there. If I know I'm looking for temperature sensors, I can navigate to sensor, look at the types of sensors. There's going to be temperature sensors. There's going to be flow sensors. There's going to be voltage sensors. I can choose the related subclass, traverse into this own sub-hierarchy, and find the class that I'm looking for. This is also a very naturally extensible structure. When I come up, if I have some very rare, some very custom points or equipment in some site, I can describe that in terms of classes that already exist within the hierarchy. If I have a new type of terminal unit that's just produced by train, for example, I can go and introduce that class under the terminal unit, as a subclass of the terminal unit class in the Brick class hierarchy. And this allows other people to find it. It also provides a very easy mechanism for multiple entities or groups to work together to create the class hierarchy, describe the set of equipment and points that they have without too many conflicts. Relationships is the other core part of Brick. This is a little bit of an abstract diagram that shows how entities of a certain type can be related to one another. So locations can be part of locations, is what this arrow on the top left means. Equipment can have the has location relationship to location. So equipment can be located in things that are of type location. Equipment can be part of equipment. Equipment can feed equipment, which is sort of the indication of a process, of the direction of a process. So, for example, an air handler unit would feed a VAV because the air handler unit is upstream. Points can control points. Points can be located within locations, and so on and so forth. So relations can be transitive. So if one thing is contained with, if A is contained within B and B is contained within C, then A can be considered to be contained within C. Things can be symmetrical. We can add whatever properties that we want to these relationships. And what the relationships do is they allow Brick to extend to cover these new settings and new equipment. The fact is, if I have an air-based HVAC system or if I have a radiant system, there is still going to be a notion of sequence that's there. And so an air handling unit will have a feeds relationship to my VAV the same way that a part of my radiant system would be upstream of another part. And so these relationships are able to port across various scenarios. Here, for your reference, and I'm not going to go over this, but this is a list of a few of the relationships that we define within Brick. This defines the domain and range, who can have that relationship to another class of object, whether or not these are transitive, and of course the definition. And so now that we've gone a little bit over the sort of the abstract structure of Brick, we'll talk more concretely about what it actually means to use Brick within the context of a real building. And so we're going to be talking about brick models. And a brick model is a digital representation of a building. It's essentially our graph that we went over before. The nodes are the things. This is our assets, the equipment, the subsystems, the class structure, and the edges are going to be relationships, indicating things like location, control, connectivity, composition, influence, and so on. And to sort of walk through a simple example, here our blue items are the things inside our building, the air handling units, the VAVs, and the points on the VAVs. We're going to add classes to that. So our graph here, the nodes in blue are the instances, the entities that are actually in the building, and the green, red, and yellow nodes are the actual classes from the Brick schema definition. And the links between them show that, for example, on the right, room 410 is an instance of type room. And then we can go in and add the relationships here that actually show how all of these entities compose together. The fact that my air handling unit is upstream of these two VAVs, I've added some points to one of these VAVs to indicate, what features it has. One of these VAVs has a damper, and we've got a point on one of those dampers. The other VAV, we've indicated that's part of a zone, that it feeds air to a zone, and that zone consists of a set of 3 rooms. And so within the context of an application, this brick model is going to represent, the set of things inside this building, the plugs, the sensors, the RTUs, the VAVs, the floors, the rooms, the subsystems, the electrical monitoring, essentially all of the assets and relationships and data inside that building. And once we have that digital representation, the brick model, we can start to write applications that can query a brick model in order to retrieve the data and configuration that they need in order to operate. And we're going to be going over concrete examples of applications later. And what queries do is they allow applications to account for the building heterogeneity. Because we have this digital representation of all the resources in that building, we can now query that model to ask, well, what resources do you have? What equipment do you have? What points do you have? How are those connected? And with that knowledge, the application can customize its behavior to that building. And this is a concept that we like to call application portability. And so as sort of a quick example of why portability is useful, say we have a sample application like indoor temperature prediction. Now, when I want to do some sort of indoor temperature prediction application, I'm probably going to have a few different methodologies for constructing that based on the type of system that I'm working with. An air-based HVAC system, radiant systems, rooftop unit systems. But in actuality, when I go to actually sit down to write this code or deploy this code, I have a different version of this application for each of these buildings. Each of these buildings has a custom implementation because their internal systems are constructed entirely differently. They still have the same sort of generic components, the air handling units, the VAV, but they're going to have custom cooling towers. They're going to have custom associations of how those VAVs are put together, how the zones are put together. They might have unusual points that give feedback into those VAVs. And so we're sort of stuck having to account for all the differences in buildings, and this amounts to essentially rewriting the majority of the logic of that application every time we want to put that onto a new building. With application portability, the idea is, the hope is, to sort of write once, run anywhere. I can have a single implementation of my indoor temperature prediction application, and using a brick model that will then customize itself to each of these buildings somewhat automatically with very little reconfiguration. And so to speak a little bit about the data model and representation, this is going to be sort of a little bit sort of under the cover, so to speak. But there's plenty of documentation on our website about this. But this is essentially how we actually represent the brick models. And so we're building ours over the semantic web technology. We use the resource description framework, which is a W3C standard for describing resources. It creates structured statements called triples. And these triples are essentially a textual form of communicating the structure of a graph. And so to look at sort of our node edge node construction before, in RDF, these are called subject and object, or the two nodes, and the relationship between them is called the predicate. Here's sort of the textual form above that, which you can refer back to later. And here's a simple example for creating a thermostat. My thermostat A is the name of some thermostat. It has the type relationship to some thermostat. And this is essentially what is called an RDF triple. And you'll be seeing a little bit of these in the further examples. And so sort of walk through what a more complete brick example would look like. Here's a very simple HVAC system. Our air handler unit's got a supply duct to a VAV with a set point logically associated with it. That VAV feeds air into a zone. That zone contains a room, and that room has a sensor inside it. And of course, there's the ducts going back up. So we're not going to model the ducts in this simple model, but here's essentially the graphical representation of those resources. My air handler unit, my VAV, my zone, and my room, and my points are all entities. Those have relationships to brick classes, so we know what their types are. And the relationships between those entities tell us the nature of how they are related. My VAV, my air handler unit to my VAV to my zone is sort of the flow of air. That zone consists of a room, and my temperature and set points are related to the entities VAV and zone respectively. Once more, I also have the hash location relationship that indicates that the zone temperature sensor is actually located within that group. And then if we go and turn this into the RDF form, not that I'm expecting you to read all the way through this, but there is a textual representation. And this textual representation is what would be loaded into a database, is what would be queried by the application, but it's not necessarily what would be pushed forward to the user. This is just the sort of the nature of the implementation of Brick. And that's all I have. I'm going to turn it over to my colleague, Jason. So should I stop my own screen share, or will you be able to handle that?
No problem. I've now changed it over so Jason can present.
Beautiful, thank you.
Hello, everyone. Can you see my screen?
Yes, we got your screen.
Thank you very much. I will present it. Okay. Hi, I'm Jason Ko, a PhD candidate as well from UC San Diego. And we have talked about the building's heterogeneity, sensor heterogeneity that blocks the way of large-scale application deployment. And now we would like to abstract those heterogeneity with Brick and building management systems or building operating system, providing APIs or data storage can rely on Brick And applications now finally should be able to discover the right resources they want from heterogeneous buildings. And now I'd like to talk about how applications actually use brick for or get what they want. And I'd like to demystify that the graph is easy to use and actually fun, and actually like using natural language. So here's a general workflow to access metadata and time series through building operating systems, or called building management systems. Users will get authenticated through an app at the building operating system, and the app, based on its logic, will try to discover what they want through metadata discovery process. And once it identifies what kind of entities that it needs to access, it will actually ask the data or time series data from the database, or try to actuate the actual temperature set point or occupancy command through resource manager at the actual network. Within mind of the general procedure, we have developed various building applications so far. Some of them are still in actively development, such as Genie as a HVAC web interface, or energy disaggregation, or visualizing energy better, and demand response model embedded inside the building operating system. And we also have an open testbed data analytics platform called Mortar. Now I want to talk about a single application as an example to explain what is the app logic and what is the what are the queries that they need to use for against brick. So brief motivation about this this application. Software thermostat is necessary because physical thermostat is usually not that easy to access and hard to configure. Schedules, set points are often hard-coded in physical thermostats. It's very hard to adapt it to the actual occupants necessary. And we may want to visualize more information, such as energy feedback or other parameters and so on. So we have deployed Genie on a building at UC San Diego for the last 5 years. And you can set the temperature, you can turn on the AC and turn off, change the temperature set point and so on. So what do you think we need, this application needs to do with brick and building operating system? It needs to just understand the room's AC status and should be able to control the AC too. So we are going to, I'm going to give you a tutorial over this simple example building. This is a subset of the building that is presented before. It has zone temperature set point associated with a VAV, and zone temperature sensor associated with a zone. And that VAV is feeding actual air into that zone. However, there's one thing that we didn't deeply discuss so far, which is actual pointers to time series data, because different building management systems or different implementations may have different ways to access time series data. We don't standardize this pointer abstraction, but this is a general workflow in any of the systems. Any entities can be associated with certain identifiers that to retrieve the time series data at actual database. So now, once you are able to discover the entities with brick, you also need to be able to get an access to database with that information. So here's the general brick query design process. So first, you need to think about what are the entities that you need against the building. Maybe there's an instances of zone temperature sensors or occupancy sensor or airflow rate set points and so on. And then you'd like to provide a little bit more information about the context of those entities. So what are the relationships of this with others? Like what is the location of this? What is the equipment that is related? And we would like to go further. The application may need to refine that information further by defining the types of that other entities. Maybe we would like to specifically look for VAV as the equipment, or HVAC zone as the location types, and so on. And those entities, that other entities related to the target entities, may have relationships with others anyway too. We may look for VAVs actually related to certain zone or certain AHU, and so on. And the list can go on. So you can provide any kind of the patterns that you would like to define your app's logic to brick query engines. And then you can get the right results over heterogeneous buildings based on brick model. And here is an actual hands-on example with Genie to get temperature. So in natural language, what is your question to get temperature? So basically it is, what is the temperature in a zone? So first you need to ask, what are the instances of zone temperature sensor? And zone temperature sensor is a brick class. I won't go over the actual details of this query language, but we use Sparkwell as an example query language. But you can use any kind of the graph-based query language to implement brick information model. So here, question mark ZNT means this is a variable that we are looking for, and LDF type means that this is an instance, and brick zone temperature sensor is a class. So this line actually means that we are looking for a ZNT variable, which is an instance of zone temperature sensor. And then we would like to provide more info, relationship about this entity. So which one among the instances actually measures a zone. So then you can provide that pattern in this query language. And you can refine further by providing the instance of zone variable. And because we are looking for a zone instance of zones, it will look like this. So this is it. And if you, this is a visualized version of the query execution, and the thought process is same. So you're looking for instances of zone temperature sensor, and it is measuring something, which is a type of instance, type of zones. So in here, we find the matched patterns, and the right variables will be returned to the querier, and that they can execute any kind of data access or actuation and so on. Here's another example of setting temperature, which requires another interaction. The question would be, what is the temperature set point of a terminal unit associated with this specific zone? Because temperature set point is not directly related to the zone, but a point of control point of a terminal units, it needs another interaction. So here, this process remains same to look for the instances of zone temperature set point, and we are looking for, and we want this zone temperature set points to be associated with actual AC unit. And we would like to specify the types of the AC unit further by specifying it as a VAB. But as we talked before, because Brick provides a great hierarchy of the different abstraction of these information, an application can choose the right level, such as terminal units, which is a super class of VAB. Because different buildings may use VAB or fan coil unit or some space heaters or something like that, if we want our app to be general enough to cover any kind of those things, we can specify terminal units instead of VAB. And we would like this VAB to actually fit in the zone, to associate with user spaces, and of course the zone should be an instance of a zone. So here's the graphical matching again. You're looking for zone temperature set points, which is a point of VAB. VAB is an instance of VAB or a terminal unit. and VAV is feeding air into the zone, and the zone should be an instance of zone. So far, we are just encoding our natural language questions into the syntax as SparkQuell syntax. So far, we have Genie, and what Genie needed was to provide the necessary types of entities that it is looking for, and its local relationships and its functional relationship with others. Because we don't limit how to associate relationship with those entities, application can be flexible as in flexible to ask any kind excuse me to ask any kind of relationships over the building, brick buildings. So not only the apps, but we have dedicated to provide all the tool chains that is necessary from in the building workflow. We have building brick optimized databases, HotDB, developed by Gabe, which is the fastest graph database for SparkQuell. Of course, there is an external tool, Virtuoso, may provide a more generic functionality for RDF storage. And you can look up Brick at the website, as well as we have a visualized version of Brick schema exploration. And more generic tool is the Protege, which is generic ontology development tool, where you can explore how the schema looks like. Also, we have Brick-enabled building operating systems. Brick Server is our minimal reference implementation of accommodating Brick data and also time series data together, providing common APIs. And XBoss is extensible building operating systems, which utilizes distributed authorization mechanism for extensible system. And we have Brick authoring tool. This is a graphical user interface that with which you can play with Brick model. You can add entities and you can remove entities, modify relationships, and so on. And we do have metadata normalization tool called Plaster, which will help you to make, convert your buildings into Brick more easily. And we have open testbed called Mortar, where you can, which contains more than 100 buildings of the data. They are all brickified so that you can send queries over the buildings and get the data and do analytics on flight. And as you mentioned, we're dedicated to develop more open source applications, and we hope that we can deliver this to any of you later. So I talked about what are the Brick applications and what is the necessary Brick tools, but one of the important tools that I would like to briefly introduce is how to convert existing buildings into Brick. And because buildings are heterogeneous, the instantiation process is highly manual. There are many vocabularies, there are lots of diverse relationships, and the building conventions are difficult for even for a domain expert to understand. So we would like to help automating the process with machine learning and several tools. This is an actual metadata that I retrieved from UCSD building. So this means that EBU3B is a building, and W hole is a hole, and ZNT is an instance of zone temperature sensor. And of course, they are related to each other. ZNT has location W hole, and W hole is a part of the building. So converting this unstructured metadata into structured metadata, here we target Brick, is called metadata normalization. So to convert one building to Brick models, we would like to reuse known mappings and other buildings as much as possible. And if there is any missing information, we would like to provide, we would like to get the right labels from a domain experts. And then finally, we should be able to convert these the target buildings into break models. And the goal is to minimize the human effort in general. So we have been conducting many research projects with this problem, and we found that there are 4 components common across different frameworks. Thus we standardize data and feature extraction stage, and inference stage, and evaluation stage, and provide Plaster as a programming interface. And we have implemented several algorithms that with it. Scrabble, program synthesis, building adapter, Zodiac, so which enables benchmark integration development of new algorithms better. The more good thing is we're currently actively developing web service, Plaster as a web service, where you can put your own building data and try to infer the right brick labels for that. Or you can interactively train a machine learning model with providing the right amount of these training examples to the system. So in this way, we would like to help users to adopt brick as soon as possible. And now I'd like to hand over the presentation to Yiyi, and she will talk about brick in action.
Thanks, Jason. Can you make me a presenter?
Yes, I can. Give me 1 second. Okay.
Thank you. Hi, everyone. My name is Yiyi. I'm a product manager at Johnson Controls. Today, I'd like to share with you guys how Johnson Controls use brick to address some of our smart building use cases. Johnson Controls is a building controls company and solutions company, so we deal with a lot of different proprietary systems and other data sources. Prior to adopting brick, it's extremely difficult and costly to navigate around all this data from all these different systems and make applications on top of the systems, and also to make them talk to each other. After discovering brick, we just really love the idea of common data representation and standardize the data we ingest from all these systems. Recently, Johnson Controls just started working with a company called BIA. It is a sustainability company in UAE, and we're creating the Office of the Future with BIA to their new headquarters building. This building is located in a desert with very sleek and curvy design. We're all very excited to work on this project. And with the help of brick and the concept of common data model, we find it's very easy to commission, develop, and deploy all these applications that we develop to enable this experience, especially comparing to old time without using brick. Johnson Controls has a very long history working in the buildings business, and we find brick very effective and expressive in the HVAC, BMS, and lighting domain. And Johnson Controls is also very strong in other domains outside of BMS, for example, security and access control. And brick has proven to be a very well-grounded logical foundation for data modeling practices. It is very easy to extend and provide consistency across different standards and systems using brick. Now let's take a look at some analytics use cases that we use for smart buildings at Johnson Controls. The first one is fault detection. This is a very common problem that we have to deal with in HVAC applications. We have to look at the BMS and HVAC equipment data to look for problems in the buildings. For example, stuck dampers. This is a very common problem that we need to detect. And brick even provides tutorials to help you query and find this kind of entities to address this kind of use cases. And Johnson Controls has a lot of similar experience working with spot detection, and bricks just make it very easy to apply the techniques to new buildings. Very similarly, in energy optimization, Johnson Controls has very deep experience with algorithms on how to optimize energy, and we model the buildings in Brick. This makes it very easy to deploy such applications in new sites, and it really helps us cut down the cost for commissioning. Lastly, risk analytics. This might be a little unexpected, but we have a product called Connected Converged Security. This application would look at data from buildings and other data sources, and it helps secure buildings. And we can understand and prioritize the threats of the buildings and update situations in real time. We use Brick to model the buildings, locations, and equipment data to create such applications. So where are we storing all this data? Johnson Controls Digital Vault is the data platform that we use to ingest, standardize, and store the data for all these use cases. We ingest sensor data through protocols such as BACnet, OPC, and we ingest location and equipment data from BIM models, BMS systems, access control systems, and other data sources. We have designed a common data model based on Brick and standardized all the data, and this data model evolves as we come across more use cases, but Brick is proven to be very well-rounded and very adaptable for designing a common data model for us. So to learn more about what we do at Johnson Controls around smart buildings, you can find information at this link. And to learn more about what we're doing with Office of the Future, you can check out more on this website. And I will pass it back to Jason.
Thanks, guys. That was really, really good. Jason, do you have any more slides to show?
No, Yiyi, can you just go to the next slide? Yeah, I just would like to finalize what we have presented. We would like Brick to be a lingua franca for building lifecycle. We don't claim Brick to be comprehensive for any kind of all the aspects of the models that is necessary in buildings, but we would like to connect different models as well as providing a ground base. Different models may include like haystack or IFC, building topology, ontology, and so on. And Brick will forever remain as community driven. We receive vocabulary extensions from various contributors, and we would like to have tool developments from various companies and research groups. And Brick could be used in any kind of the workflow among any kind of workflow inside buildings, such as device development, building commissioning, system integration, app development, and so on. Thanks for listening to us, and we'd be happy to receive any questions, and please visit us and share your thoughts. Thank you. Yeah,
thank you, guys. That was an excellent presentation, and there's a lot to, I'm sure, for people out there to unpack. But of course, we have recorded the session, so it will be available for everyone to listen again, and the slides will be made available. And I think Gabe said earlier that they would be on the website there, brickschema.org, and I'll certainly be putting them on our website as well. I hope we've got time for a few questions, if that's okay. I've had a couple come in for you guys. So maybe this is first one here for, let's say, for Gabe or Jason. You have mentioned that a potential function of Brick is representation of assets. How can Brick be used with BIM, building information modeling, during design construction, and with CMMS after the construction is completed? Do you guys have any thoughts on how it can play with, for example, a BIM model?
So we have a little experience integrating Brick with BIM models. We actually have a project that's going to be funded by the Department of Energy to perform some of that integration. What we imagine is that we're not going to supplant IFC or BIM models with Brick, but what we can do is, because there's already so much tooling and people are already used to IFC, and I don't think we're going to do a better job of IFC than IFC. But what we are going to do and what's coming up is performing an integration so that it's easy to go from the design and construction phase with your IFC model and your BIM into Brick, so that there's less of a sort of impedance mismatch between those. I wasn't familiar with the second system that you mentioned, CMMS.
Yeah, that's what they said. I'm not something I've heard either. But I guess, I mean, in the context of, let's say, maybe some kind of CAFM or facilities management software, how do you see, for example, Brick helping to manage the building, you know, throughout its life cycle, not just during construction?
Yeah. So, I mean, Brick as a data model is very extensible. And what we have been doing is where Brick is sort of an integration piece between many different pieces of software. So if I have an identifier for a time series database or an ID for an asset in a BIM model or some asset tracking software, that can be represented within a Brick model. And so I can go to my Brick model, I can find my pointers to my resources in other pieces of software. And so we don't have a whole lot of that fleshed out, but I don't see any problems in any sort of fundamental problems in performing that integration. One thing I will plug is on the brickschema.org website, there is a link to GitHub issues page as well as a Google message board. So if you do want to dig into more of these questions with the Brick Consortium team, that's probably the best way to do it.
Mm-hmm. Yeah, that'd be great. Oh, it's been clarified, by the way. CMMS means Computerized Maintenance Management Systems.
Okay.
Yeah.
I'll do some more homework.
And I think, you know, on that point during the presentation, it was really interesting to see that, like you were talking about them using machine learning to kind of, in a way, you know, like look at, like as you said, like one of the main problems is the fact of all the buildings out there who have all of these, you know, different older systems, and trying to be able to understand those and convert that into a more structured Brick, you know, model. I think that's super interesting. So it's great to see you got some tools to help people to do that. Very interesting. Another question here: what is the progress at the ASHRAE BACnet level? When would we expect to see the first public versions which incorporate and harmonize Brick and Haystack? Is that something that you guys are working on? I remember reading something earlier this year about a potential new ASHRAE standard.
Yes, so the ASHRAE 223P standard is under development. In terms of the timeline, you'd have to ask the people that are the ASHRAE members that are sitting on the committee. But I can say that it feels like we've made a lot more progress in the past year. So we're working very closely with Brian Frank from Project HVAC, as well as the Brick team and the people from ASHRAE to sort of integrate the models. Another person who's been very helpful is Joel Bender from Cornell University. And so if you were to ask me what my sort of guess at what the standard will look like, it would be something like you'd have tags that would appear sort of on the equipment as they get distributed, but you would have a richer data models looking similar to Brick that would help tie those tags into concrete types and encapsulate the relationships and all the rest of that. So tags are very nice because they're very small, they're very efficient to put on these sort of constrained embedded devices. But you do need a richer, more expressive data model to actually get, you know, the insights into how the building's supposed to be put together and how these equipment fit together. So I don't have any sort of a timeline, but we are all working together, and we are making progress.
Good. Okay. Well, we can wait out on information exactly that, but I'm sure once it's done, it will be released. A couple of final questions here. Is there an aspiration to grow Brick to other sectors of the built environment? They're using as an example here, rail, roads, aviation. So I guess maybe you know, a smart city scenario. Can you see a potential for expanding outside of buildings?
Yeah. Our Brick model is, as we have argued before, extensible to accommodate any kind of other vocabularies in other domains too. So we have experimented on our UCSD campus to accommodate other types of the data other than just buildings, such as traffic information, and as well as parking information, and other street light energy sensors, and so on. We found it is successful. It is easy to extend Brick to other domains, but we need more concrete agreement with the expertise in that specific domains, and we'd be happy to receive any kind of contributions or suggestions to extend it to other domains. Because we started from HVAC modeling because we have the easy access to those data, but we would like to see real data to finalize our modeling is good for other domains too. So we'd be happy to talk.
Good. And on that note, I guess we can say, if somebody was wanting to get in touch, we've got the website there, brickschema.org. And if there were more questions, is there a way to get hold of you guys? Are there contact details on the website?
Yes.
There is a link to the Google group. Sorry, Jason, go ahead.
No. I mean, you finalize it. Yeah, that's what I wanted to say. Yeah.
Okay, good.
So we have Google Groups links at brickschema.org. We can have conversations there, but we also receive GitHub issues. If you need to contact in private, you should be able to find the emails at the Google Groups too.
Great. Well, I just obviously want to say to all three of you, thank you very much for sharing that information. I think it's extremely interesting and a project that I think anyone who's to do with smart buildings and should keep an eye on. And if you are developing applications or commissioning integrating systems, it's well worth keeping an eye on what they're doing with Brick. So beyond that, as I said earlier, we've recorded this session. So I'll be posting it online later today, so feel free to share that with colleagues. And then beyond that, we've got some more interesting content for the Smart Building series coming up next month and September as well. So keep an eye on the Memoori website for all that information. So just remains me to say thanks to Yiyi, Jason, and Gabe. Again, thanks guys for contributing today. Really interesting.
Thank you, everyone. Thank you very much for listening.
And of course, thanks to everyone for listening. And hope to speak to you all soon. Bye-bye for now.